actually going to disassemble a C program to see a little bit more of like what happens underneath the covers as a process or a program gets executed in an operating system. So if you look at my terminal, we have a very simple test file that we have. So there's a main, there's a variable called x which has 10, and then we're incrementing x by 1. Then we are calling this function foo, which also increments x by 1, and then we are storing that value back in x, and then we are returning. So it's a very, very simple application that we're looking at. And what I want you to sort of like think about is like, like when this application actually runs, like what are all the different hardware pieces, at least, that it touches, like what happens in the processor as this goes along. Right. So what we're going to do is we're going to disassemble this, right? So so in this particular case, what is happening is that we are going to look at the assembly code for this file, and so that's what the S flag here means. And we're going to cut out some of the other stuff that usually is produced by using this compiler option. So let's actually do that. And so we have test.s. And if you look at it, right, it's a very simple, somewhat readable file, and this is what assembly looks like. So the file that we're looking at is test.c. In C programming, you would have learned about like global variables and functions. So foo is a globally defined function, so it comes up here. We have first the what happens in foo, and we can look at this like side by side with the code, so that you have a flavor of like what's going on, right? So in previous units, we have talked a little bit about like how every time you call a function, there has to be a certain amount of saving of state that goes on, right? So if you look at my iPad, let me actually sketch what happens here, so that you have some context before we go into the program. So to remind you of what goes on, so we have a processor, and we have some memory. Okay, so as you execute each instruction, there is an instruction pointer, right? So for example, let's say we're going to do popq, right? So this is one particular instruction. So the instruction pointer has to point to this instruction, and that instruction pointer is in hardware, right? So that's one piece that has to point to it, right? And then what we're accessing here is RBP, which is a register. So there is a set of registers in your processor, right? One of which is this particular register, which has to be stored in hardware. It's hardware state. And then, for example, when you say you want to access like location 10 or something like that, that is actually a reference to something in memory. And so that is also something that needs to be accessed, right? So apart from this, do remember that when you're doing pop and push and everything like that, there is a stack, right? Which, as I mentioned previously, grows downwards. So this is high memory, this is low memory, and then it grows downwards. So that is a stack. And so every time you execute a function, right? So the function uses a set of registers. The function will change the instruction pointer, and the function will have its own context, right? And this context is stored as a stack frame on the stack. Every time you call a function, there's a new stack frame that is created, which contains all of the values. In the particular example that we're looking at, in function foo, there is a variable x, which is local to that function, right? So which is actually on the stack, right? So and when you return from that function, unless you actually save that value as a return value, the x value goes away. That's because it's on the stack, and then when you finish that function, you throw away the space on that stack, right? So long story short, when a program is executing, there is the instruction pointer, which is the current instruction that is being executed. There is a register state, which shows like EAX, RBP, all of the registers, like what's in that value. There is memory that the application has modified, for example, in the stack. and then in the rest of memory. But specifically, the stack is very local to this particular process, right? So it's not global, like only this process knows about the stack. Every function that's executing, it uses the stack and so on. So hopefully this gives you sort of like a feel for like what happens when you actually execute a function. So now actually let's go back to our terminal, and then hopefully this should make a little bit more sense. So when you execute any particular function, let's say foo, right? In this case, when you start executing a function, you have to create a stack frame for it, right? And you have to save the current state before you can actually start playing around with the state inside that function. And that's really what these instructions are doing, right? So what it's saying is like on the stack, push the current base register, which is the start of the frame, and then move the stack pointer, which is like the start of the new frame, into the base pointer. So if, let's say I wanted to do comments, right? Like save existing function state, and then move to start of frame for new function, basically. That's what this is doing, right? And again, like, so at the end, right, when you're doing this pop, like what you're doing is restore existing function state. So why do we save and restore and all of this stuff, right? Because when from main, when we call foo, we don't want to lose the value of x here, because this value of x is local to main, and we don't want to lose that. And so we have to store that state somewhere, and which is on the stack. And when we come back from foo, we once again want access to that state. And that's really what this is doing, right? So it's saying save existing state, start executing within this function, and then when you're done, restore existing state. And if you look at the actual code itself, like the assembly instructions, this is stuff that is somewhat easy to understand. For example, you're adding 1 to x, and then that is actually what is going on here. And we are saying there's a relative value here, like -4 from the base pointer. And the reason for that is the argument, right? So x is an argument that's coming in, and we are incrementing that argument. That's where the argument for this function is stored, 4 bytes lower from RBP, right? And in the end, we want to return x. So whatever is the value of x should be in the register EAX. And this is something that is handy to remember. In all functions in x86, at least in 32 bits, the return value will be in register EAX, right? So here the value is being stored in EAX, and then it's returning from foo. And if you look at main, it's pretty much the same, except that we're actually calling foo, right? So there's a one-to-one correspondence between the code that you write here and the assembly code that is generated by GCC. And looking at the assembly code reminds us that, like even though this looks very abstract, in the end, there is a physical machine with registers, right? And your application has to be transformed into something which says, put bit here 1 into this register, put bit 0 into this other register, and that's how really your applications execute. Now, remember, the reason I'm showing you all of this is to say, when you have multiple applications running, as we saw previously, when you have both hello and world being printed on the same time, on the same processor, this is all the stuff that the operating system has to take care of, right? So if you're running the hello program that has its own register state, its instruction pointer, its state on the stack, and so on. The world program has its own, instruction pointer, register state, and so on. So how do you actually run both seemingly at the same time on the same operating system? This is something we'll look at next.